Hello, everyone. It's a pleasure to be here at New Ideas in Network Systems. This is the perfect venue to talk about something that is often overlooked, yet absolutely a fundamental problem to the internet nonetheless, partial reachability, and how it directly ties to what the internet intrinsically is. I'm Guillermo Baltra, and together with my colleagues, we are excited to share our work understanding partial reachability in the internet core. In essence, our work is motivated by network measurements. We study outages because they provide a window into what is actually happening in the real world. Take the 2024 unrest in Bangladesh. The government implemented a total internet blackout for 5 days in response to widespread protests. And just weeks later, we again observed a second phase of nationwide shutdowns amidst the government's resignation. Like us, many groups have built their own outage detection systems, and every single one of them has implemented their unique understanding of what an outage is, with different compromises, especially when multiple observers have different opinions of whether a site is reachable or not. For years, partial reachability has been the blind spot of outage detection. Most current solutions either rely on simple majority voting or throw away conflicting data entirely. The fundamental problem we're facing is that there is no established theory to explain why these different vantage points see different things. This is exactly what our work aims to address. Our work makes three main contributions. First, we provide a clear definition of what the internet core is, and just as importantly, what it is not. This gives us a principled way to talk about global reachability without relying on ad hoc labels like Tier 1 or on assumptions baked into specific measurement platforms. Second, we develop algorithms that operationalize our definition. And doing so resolves cases where observations appear contradictory. With our framework, these aren't contradictions. They are partial reachability states that we can now identify and explain. Third, we apply this definition to real-world data to characterize partial reachability internet-wide and improve precision of other measurement tools. As I said, we care about outages, which has led us to a fundamental question. If outages are disconnections, then disconnections from what exactly? What is the internet? Early definitions of the internet made emphasis in the interconnection of networks, sometimes considering universal data delivery and a shared address space. And even though all of these are good properties of the internet, however, they are not operationalizable in the sense that we want our definition to enable us to measure and quantify when the internet is and when it is not. Today, the internet is totally different from the 90s. Most users access through their phones, going out through a NAT device. And most of the time, they're probably not connecting to a dedicated server anymore, but to a service in a cloud, which is probably also behind NAT. So there are all these kind of mappings going on. And the particular question we care about is, how can we address all the political and technical challenges that have arisen, especially in the last decade, that challenge universal reachability in a single global internet core? Here's the definition we propose. The internet core is the set of active IP addresses that can bidirectionally route to more than 50% of all public potentially routable IP addresses. This definition is conceptual, independent of any specific measurement method, yet it gives us a clear benchmark that operational systems can approximate, and it lets us reason cleanly about corner cases. Why the 50% threshold? Because it guarantees a single majority component with no need for a central authority or predefined tier 1 list. The core becomes self-defining, simply the largest group of networks that continue to talk to one another. If a country or cloud isolates itself, it hasn't broken the internet, it has just moved outside the majority component. Why bidirectional routing? To capture the core internet principle of universal data delivery. Different systems can measure reachability in different ways, ICMP, TCP, HTTP, but the requirement itself stays at the IP layer where it belongs. Why public potentially routable addresses? Because they form the globally unique address space the internet depends on. We treat all public IPs equally, consistent with the internet's flat, non-hierarchical design, and we exclude private or not hidden space, which functions as a second-class domain outside universal reachability. Finally, why active addresses? Allocated or theoretically routable prefixes aren't enough. If an address never appears in routing, never responds, never sends or receives traffic, it's not part of the internet's actual functioning fabric. This is especially important in IPv6, where most of the space is unallocated or unrouted. So we restrict ourselves to addresses that are alive today because that is the internet that actually exists, not the one that might exist someday. Our internet definition highlights the internet's rough edges, like intentional partitions and peering disputes, and that some network configurations occur as a result. We call these network configurations islands and peninsulas, and we further have the data to show them. For islands, ASD in the figure is cut off by a local failure. E has public IPs but never announced routes. Both exist, but neither is globally reachable. For peninsulas B and C, they can reach many others, but not each other, still attached to the core, but only through asymmetric paths. In an outage like X, there are no active addresses at all. Powered off systems vanish entirely, unlike even a single laptop, which forms a tiny one-node island. This taxonomy lets us distinguish real outages from routing asymmetry, isolation, or policy-driven splits, a far richer picture than simple up or down. Islands occur whenever computers are not reachable, as in cases D and E from our diagram, and importantly, islands are far more common than true computers off outages like X. Anytime a portion of the IP space becomes disconnected, even if the devices remain powered on, we get islands. A concrete example is the CenturyLink backbone outage on 2020. During that event, customers' machines or local LANs could still talk to each other normally. The break is in the connectivity, not in the endpoints themselves. Islands look like outages to observer, but the computers are actually fine. Peninsulas occur when two locations can reach each other, but each of them can reach many others. Their connection to the core is limited. This is the situation we saw with the SSB and C in our diagram. There are short-lived peninsulas as documented in Internet Optometry back in 2009 as short-lived asymmetries and reachability gaps caused by routing dynamics. But some peninsulas aren't fleeting. They persist for hours, days, or even years. Common causes include ping disputes, routing misconfigurations, and firewalls. To detect and measure both islands and peninsulas, we have designed two algorithms inspired by our definition of the core, Chiloé and Taitao, names from the Patagonian geography. The idea behind Chiloé to detect islands is simple. If you lost reachability to more than 50% of the internet, you are sitting on an island. You have left the internet, which nicely ties directly back to our definition of what the internet is. And a positive externality from this approach is that From a single box, you can test whether you are part of the internet or not. Our peninsula detection algorithm is called TiTau. As I said, peninsulas occur when portions of the internet are reachable from some locations and not from others. So if we have vantage points located in different places, they can have different opinions whether a target block is reachable or not. When we have that difference of opinion, that disagreement, we can detect peninsulas. So we continuously measure the internet, evaluating reachability to each block from multiple vantage points. When there is a disagreement between vantage points, then there is a peninsula. To validate ITAO, we source data from Trinocular's 6 globally distributed independent vantage points and a broad IPv4 coverage. We compare our results against ARC, another measurement system with a larger number of vantage points. Without getting into much detail, we get pretty good recall. What we see is true, and we get a good number of true positives and true negatives. In terms of results, there are two key ideas I want to convey. First, how many independent vantage points do we need to measure the internet to get unbiased results? And the answer is around 3 or 4 sites, you can get a pretty good view of what the internet looks like. And that is important because we can't measure from millions of sites. So to test this question, we vary the amount of sites we combine. On the graphs moving to the right uses data from more and more observers. The left graph is how much of the internet is reachable, and the right graph is how much of the internet is unreachable if everybody has to agree. And the key point here is on the graph of the right, it converges after about 4 sites were pretty much on the flat line of the slope. The other key result is peninsulas. How often do our 6 sites disagree? The key thing to observe here is that the scales on the graphs are exactly the same. And roughly the number of peninsulas we see is equal to the number of outages. So many measurement systems are worried about outages and not about partial connectivity, but peninsulas occur just as much as outages, which confirms that peninsulas are a problem that does matter. Finally, I want to share with you an application of partial outage detection. DNSMon monitors reachability to the root DNS servers on top of the right Atlas infrastructure. But for years, DNSMon has shown that IPv6 reachability looks consistently worse than before. Right Atlas operators are aware of these problems, which occur because some vantage points support v6 on their LAN, but not to the global v6 internet. Now, here's the core issue. DNSMon didn't originally account for partial outages. Atlas periodically tags and calls these vantage points from DNSMon. However, the number of unanswered queries remains high. So is this problem fixable? To answer that, we apply our island and peninsula definitions to DNSMon's underlying measurements. What we found is that islands account for roughly half of v4 problems and most of the v6 ones. At least one root server operator was on a peninsula and is explained by routing dispute between cRoot's operator Cogent and Hurricane Electric. This example shows how understanding partial reachability can improve sensitivity of existing measurement systems. And removing islands makes it easy to identify persistent routing problems, and removing peninsula makes transient changes more visible. To conclude this study, we show that outages are not black and white. Partial connectivity exists, and it is as prevalent as outages, and that formalizing the definition of the internet core allows reasoning about current challenges facing the internet. We unpack this definition and propose different operational algorithms to characterize partial reachability. We further provided a practical application for our algorithms. And I want to finish with this question for you. How does this definition help clarify your inner challenges? Thank you, and please get in touch if you have any further questions or comments.